Welcome. In this video, we're going to discuss about inverse Z transforms. Okay, the generalized form that given xz, how do we find x of n, right? Given xz, how do I find x of n? This is the formula, but how do we derive it? Let's do it for with a simple proof. For example, you know already that basically what is xc? xc is the DTFT of xn r to the power minus n, where r is your some constant. As you know, in the xy plane, it's the radius of your or distance of the complex number from the origin. Basically, z is equal to r e to the power j omega. So DTFT deals with e to the power j omega. If we add this term r, so it becomes Z transform. Okay. Now, how do you write DTFT or inverse DTFT for xn r to the power minus n? Inverse DTFT is given like this. This is the time domain signal or the samples. And this is x e to the power j omega, e to the power j omega d omega. This is the inverse DTFT of this x, which is basically not e to the power j omega, but r e to the power j omega. So this thing is z, right? So the inverse z transform of this thing is given by this. Inverse DTFT is given by this, right? But we know that z is r e to the power j omega. So I can replace my e to the power j omega n with z by r to the power n, right? It's simple. Now the next term is d omega. Now I have to convert my omega into r, basically d omega to dr or dz. How do we do that? We go back to this formula. We see dz is r e to the power j omega times j times d omega. So from here I can derive the value of d omega in terms of dz, right? So r e to the power j omega is z. Now I substitute these values here, and what do I get? But before I do that, I know these limits are from minus pi to plus pi. This is there when I am moving in a unit circle. Unit circle means that my r is 1. Right? But now if my r is not 1 but is any other arbitrary value, then it's basically a counterclockwise closed path at mod z equal to r. Basically a circle with radius r is fixed in this case. And this circle should lie in the ROC, right? Because you know our r should lie in the ROC for convergence to happen. So since ROC is mentioned, is specified with x of z, so you definitely know the ROC. So you choose your closed path inside the ROC with fixed r. Okay, now let's substitute these values here. So what do we get? So this becomes x of z. This becomes z to the power n minus 1 because there was a z in the denominator here as well. And so that's what we get. And if you compare the two terms, r to the power minus n is constant, so they can be taken away. So your x of n is basically the inverse z transform of this thing. So this is how we can understand this inverse z transform. To solve this integral, we can use Cauchy's integral theorem. I'm sure you must have read it in your MTH course. I think the second course, MTH 102 probably. But we won't discuss this that part in this course. So we won't be dealing with Cauchy integrals or integrating in the z space. Okay. So what kind of methods shall we be using in this course? Mostly they will be by inspection. What does that mean? So you know the standard forms, right? What are the standard forms? You know delta n is 1 and delta n minus m is e to the power minus m. This is one standard form, very popular. Another form is 1 upon a z inverse, this kind of form. Basically, which means you are, these two are pretty much standard forms, and if you remember them, you can find most of the inverse Z transforms that we will be requiring for this course. Okay, so you know this already. Now you know the properties of Z transform. If I do a shift in the time domain, it leads to a multiplication in the frequency of the Z domain. If I do a multiplication in the time domain, it becomes basically a scaling in the Z domain. In this way, you know all these properties, so you can use these properties to find inverse Z transform. Okay, we'll look at some examples. So for example, this complicated looking form of xz, given the ROC is mod z greater than half, how do you solve for this? So if I just compare it with what I know, it looks like 1 upon 1 minus az inverse kind of a form. And there is a square, so obviously we can very easily attain it if I differentiate 1 upon 1 minus az inverse, right? So let's start. We already know xn for 1 upon 1 minus half z inverse. This is our simple thing, because we know it's a right-handed sequence, mod z greater than half, so a to the power n un, right? Now we can use the derivative. If I differentiate this, what do I get? I get a square in the denominator, and that's it. And if I use this, I can very easily derive the form of xn. Okay, so the next method which I can use to find inverse Z transforms is power series expansions. What does that mean? It means if I am given xz, it is basically x of n z to the power minus n, summation over all n. If I can expand xz in terms of z to the power minus n, and I can compare the coefficients on the two sides, then very easily I can find out x of n, right? If we can express xz as a power series in z to the power minus n, then we can find xn as their coefficients, right? Now, how do we do that? How do we express xz in terms of power series? One method which you of course know is the Taylor series expansion of xz, right? You can do a Taylor series expansion. Or if xz is a rational polynomial, then you can use long division. We'll see some examples. What does that mean? Example 1, you have xz in this form. Xz is 1 upon 1 minus az inverse, and the ROC is mod z greater than mod a. What does that mean? This means this is a right-sided sequence. Since xz exists at z going to infinity, we only want z to the power minus n for n greater than equal to 0 terms in the expansion. So we cannot afford to have z to the power minus, or basically if my z goes to infinity, it should converge, right? This means infinity to the power positive will make it diverge, so infinity to the power negative will make it converge. So therefore, if this is infinity, if z goes to infinity, then n cannot be positive, and even n cannot be okay, 0 is fine because we take limiting case. So let's try to solve this. So I know basically I have to do this long division, and in the long division I only want z to the power minus n terms. I do not want z to the power any positive term. So okay, let's carry out this long division. So I have to divide 1 with 1 minus az inverse, right? That's what I want to represent in terms of a polynomial in z to the power minus n. Okay, so how do we do that? Now I want in my uh, uh, quotient here, I can only get terms which have z to the power minus 1. Like positive powers of z are not allowed. So what can I do? First, okay, I start with 1 because I can straight away cancel this. So I get 1 minus az inverse. What is the remainder? The remainder is plus az inverse. Now to finish this, I know I can multiply with az inverse because it contains z inverse. So there is no problem because z inverse is allowed for a right-handed sequence or for a sequence which has infinity in the ROC. And if I do this multiplication, this is what I get. And this is an extra term, okay, the remainder. Now I further divide it, and in this way I keep going and I get the sequence. So what I get is, I'm sorry, it should have been 1 upon 1 minus az inverse is equal to 1 plus az inverse plus a square z power minus 2 plus so on. So in this way I am able to represent my xz in terms of the coefficients of z to the power minus n, or a polynomial in z to the power minus n. So now my xn is simply by comparing the coefficients. So my x0 will be 1, coefficient of z to the power 0. My x1 will be a, and my x2 will be a square. So basically what I'm getting is xn is e to the power n, and this is valid only when n is greater than or equal to 0. So that's what I get, right? Let's take another example. As soon as you talk of ROC mod z greater than mod a, immediately question comes to mind, can we do it if mod z is less than mod a? So let's see that example now. Now in this case, my xz will exist when z goes to 0, right? Because 0 is also there in the region of convergence. So therefore, we want only z to the power n terms where n is greater than or equal to 0. What does that mean? Negative powers of z are not allowed, because if n becomes negative, then 1 upon basically 0 to the power anything negative will not converge. It's meaningless. So that's why I cannot have any negative powers of z. Now I have to carry out this division, long division, in such a way that I do not get any negative powers of z. Okay. And anyways, you know, this is a left-sided sequence. So let's see the division now. So you have to divide 1 by 1 minus az inverse, keeping in mind that only positive powers of z are allowed, right? Okay, how do I do that? If I multiply this with 1, I will get an az inverse in the denominator, as you saw in the previous example. And then getting rid of az inverse is difficult, right? Because then I have to multiply with az inverse. I do not want that. I cannot afford that. So let's try the other way. I use this az inverse, multiply it with a z, okay, times 1 upon a, to get a 1. And that looks like a possibility. So if I multiply it with minus 1 upon a z, this term, then the product will be 1, and this product will be positive power of z. So this is what I get. This thing multiplied with this gives me 1, and this thing multiplied with the first term of it gives me 1 upon a times c. Now what do I do with 1 upon a times c? I have to multiply, so now I'm keeping this first, right? So I have to multiply with this with z square to be able to get z power 1. So I multiply this with 1 upon a square z square to get this term, and then this, when it multiplies with 1, you get this term. So, and this is the remainder, and I keep going in this way, keeping the second term in the first, and I get a perfectly fine series. So this means 1 upon AZ inverse can be represented as minus A inverse Z plus Z square plus Z cube, and I can compare the coefficients to find the value of xn. Xn is the coefficient of z to the power minus n, so which is minus a to the power n. So see, z to the power 1 is minus a inverse, z to the power 2 is minus a square, z to the power 3 is minus a cube, so x3 will be minus a cube. So this is what I get, xn is minus a to the power n, and this is true for all n less than minus 1, right? Because we are considering z to the power minus n, so n has to be less than 1, minus 1. So this is how I obtain the left-handed sequence now. So in general, it can be written as minus an u to the power minus n minus 1, simply from this form. Okay, so these are the two examples which give you a very good understanding of long division method. Now another method which is used for finding inverse DTF, inverse Z transform, is partial fraction expansion. Okay, what does that mean? I'm starting with one example because you can read the general forms and get confused, but with examples you will get much better understanding that why are we doing certain things. If I give you an xz of this form where there are two terms multiplying in the denominator and you individually know 1 upon 1 minus az inverse and 1 upon 1 minus some other az inverse, you individually know their inverse z transforms, but what do I do if the two come together in the denominator? And ROC is also mentioned here. It's a right-handed sequence. Now, can we expand this in terms of something with the first term in the denominator plus something with the second term in the denominator? If I can do it like this, then I can definitely find inverse z transforms for both these terms, and you know that since z transform is linear, so inverse z transform of individual components can simply be added to form the inverse z transform of xc. Okay, so how do we do that? All of you have read partial fraction expansion in the past, but even if you don't remember, do not worry, we'll discuss it all over once again. It is very simple. Now let us say I want to find a1. What you do is you multiply both sides with this term and you put this term to be equal to 0. What will happen? Xz times this term into 0, xz times this term will give you a term where pole and 0 are getting cancelled, in other words, and you're getting this term which is some non-zero number. Now on this side you're getting a1, which is again a non-zero number, but on this one, for this term, this will become 0, because if this is 0, then this will become 0. This, you get rid of this. So basically you simply get a1 is equal to xz times this term when made equal to 0. So in other words, a1 is simply xz times 1 minus 1 by 2 z inverse with z put equal to 1 upon 2. Right? This will give you the value of a1. So simply if I now put this form of xz, what do I get? I get 1 upon 1 minus 1 upon 4 z inverse. Now I substitute the value of z to be 1 upon 2, and so 1 minus 1 upon 4 times 2, because z inverse. So 1 minus 1 upon 2, so it becomes 2. Right? Now let's see the other term, a2. a2 is xz times 1 minus 1 upon 4 z inverse when z put equal to 1 upon 4. Right? Now the a1 term will get cancelled. So this is what you get. You get minus 1 now. Now you substitute back the values of a1 and a2 and you get xz can be represented as 2 upon this term minus 1 upon this term. You can verify it by again taking the denominator common and solving, and you get the same form of xz. So but now the advantage is that you can take IDFT for each of these terms, and that will give you the IDFT of xz. So hence my x of n is basically 2 times 1 upon 2 to the power n un minus 1 upon 4 to the power n un. Why un? Because this is a right-sided sequence, which means the ROC is outside both the circles, mod z equal to half and mod z equal to 1 upon 4, right? Okay, so let's go to some generalization. We have seen xz. So basically, if you get xz in this form, basically the denominator has got so many terms which are multiplying together, n times, means n terms, capital N terms are there, and the numerator has got, okay, terms multiplying, but capital M, and capital M is less than small capital N, because you want to get terms in the denominator where basically you want to do partial fraction expansion. That's why you need capital M to be less than capital N. Okay, this is the general form of what we saw with the example, and we can express it in the form of some ak coefficient divided by 1 minus dk z to the power minus 1. Here, so one thing which you have to notice is all these dk's are different. Like dk is not equal to dk dash when k is not equal to k dash, right? And then you know how to take the inverse z transform of this whole thing. And ak you can find using the formula which we just derived. Now let's consider another example. Now, if my xz is a rational polynomial of this form, how do I do it? Now it is not, it's no longer a product of 1 minus some az inverse multiplying with some other 1 minus some other a2 z inverse, but now it is a proper polynomial. How do I do that? So basically you factorize it, find the roots and express it as the form which was given. So simply it becomes the same form what we had also seen in the example, in the previous example. So you find the roots and factorize this thing into simple these terms, right? And then you use ROC to find the inverse as we did in the previous example. Okay, case 3. Now look at this example. What happens here is now I cannot factorize it in terms of two terms. The reason being my numerator has got z to the power minus 3, the degree 3, but here degree is 2. So since m is greater than or equal to capital M, we won't be able to reduce it to case 1. So what do we do? So okay, get rid of these extra z terms. Basically, if I do long division to make m less than n, then I'm good to go. Okay, how do I do the long division? Okay, it's very simple. Basically, you write down these terms. Now, you want to get rid of this z to the power minus 3. So, okay, I multiply this with z to the power minus 1 to get something interesting. So what do I get is basically get rid of the first term and the second term remains. Even in this term I see now m is equal to n, but that is also not acceptable. M should be less than n. So I again multiply this with some z to the power 0, basically 2 times 1. So to get this term, and what do I get? It's very simple. I get, now here, if this is my numerator, then I am fine. Now my m is less than n, right? So this means now I can write my xz as the quotient 0 to the power minus 1 plus 2 plus the remainder upon the divisor, right? I can express it like this. I know the z inverse of 0 to the power minus 1, you know, delta of n minus 1. I know z inverse of a simple 2, constant 2. which is delta n, and I know the z inverse of this thing. How? By doing what is it, partial fraction expansion. So expand with partial fractions, and you get xz as this. Right? Now you can use your ROC to find the value of x of n, because each term in x of z is now a known something of known form, so you can easily find the inverse z transform. Okay, ROC is given to be mod z greater than 1, so this means my z inverse will be x of n, so delta n minus 1 plus twice of delta n plus 8 times, since this is a right-handed sequence, so 1 to the power n un, and minus 9 times half to the power n un. That's it. Okay, so these are some of the, this is the reference for this section, inverse z transform.